In this video, I show you how to compute area and lengths in polar coordinates. Consider the region OTS bounded by the rays theta equals alpha, theta equals beta, and then r is a function of theta. Let's approximate the region with n non-overlapping circular sectors based on the partition P of the angle TOS. Now, each such sector then will have a radius, which is found by evaluating the function at some angle in that particular angle range, and there's a central angle, the change of theta sub k. Because of that, we can find the area of that sector because it's just 1/2 the radius times the angle. That's 1/2 the square of the function at the angle, evaluate the change of the angle. All this is in terms of this kth subinterval. The area of the region then is approximately just the sum of these areas, and that gives you a summation. Now, assuming that the function is continuous on the interval from alpha to beta, we expect this approximation to become better and better in the limit. So we'll say that the area is therefore the limit of this particular summation. You should recognize that as a limit of a Riemann sum. So the area of the region between the origin and the curve r equals f of theta, when the angle is between alpha and beta, provided the function is non-negative or non-positive, that f is integrable, so the definite integral exists, and that the overall angle range is positive, but at the same time less than 2 pi, would just equal the definite integral from alpha to beta of 1/2 the function squared d theta. Now, these conditions are all here to guarantee, or at least to try to guarantee, that you don't wind up adding up the area twice by tracing the same curve multiple times. Also, to make sure that you don't add positive area to negative area somehow and have it cancel. Now, as an example, look at this function r equals 4 times 1 plus the sine of theta. I've given a graph for you. Now, as a point on the curve sweeps out, the ray then would sweep out the area. Notice that because of symmetry, I only need to go from one angle range to another. So that angle range is begun and ended at these 2 points. Those points are 0, negative pi over 2 and 8, pi over 2. Now I picked that angle range because therefore if I start at negative pi over 2 and I let the angle increase, I'll wind up sweeping out the right hand side of that picture. The area then is just double that area. So I'll start from the angle negative pi over 2 to pi over 2. Now, so that would then mean then that the area overall will be twice the integration from negative pi over 2 to pi over 2 of 1/4 times the quantity 4 plus So that means to find the area, we just double the integration from negative pi over 2 to pi over 2 of the integrand, which is just 1/2 the function being squared, d theta. Then just go through a process of integrating that. So we have to square it out, and I distribute the 1/2 and the 2 to cancel. And then I distribute the 16 through, and I also change the sine squared using the half angle formula. I then multiply the 16 through that fraction to get an 8, and the 16 become a 24. And then I have a minus 8 cosine 2 theta. Each of those pieces are easy to integrate, which I do. I evaluate each at the bounds and subtract them. That's the answer. That would then be the total area of that region, bounded by that curve. Now, if you want to find the area between two curves, it's very similar to what we do in normal Cartesian coordinate system. We're going to assume that we have that the radius, the region, is going to be defined by between two curves. That's why the r is between two different functions of theta. And the angle range will go from alpha to beta like before. We'll assume similar conditions, that they're both non-negative, that they're both integrable, that the overall angle range is positive but less than 2 pi, so we don't wrap around too many times. To find the area, you literally just find the area of two regions and subtract them. And since the two formulas are so similar, you can combine it to be one integral. But because of the conditions though, it's actually pretty easy to make a mistake here. Because you have to remember that every single point has many multiple representations, and you might think that the point you're looking at has one representation when it actually has another. So it might be sometimes similar to think of it as two separate, not overlapping regions and just subtract their areas. That way you can be careful with it. Let's find the area within the circle, r equals 4 times sine of theta, and above the line, r equals 3 times the cosecant of theta. To do so, notice that as I allow the point to move along the circle, eventually we will hit this one intersection point right here. When that happens, then there's a small segment that sweeps out the region. Now that small segment is actually the difference in two radii. So then I begin to sweep when I get to this point, and I stop sweeping when this point reaches this one. So to go about finding what those points are, there they are. And you can see the angle range for the top one's easy. It's just pi over 2, since we're going from 0 and up. But the first angle range, that corresponds to that point of intersection. I have to know what that is. Now we'll just use the normal technique of just setting the r is equal and seeing what happens. If you do so, you get that equation. You can then multiply both sides by sine and divide by 4. You can then take square roots. So the sine of theta must be one of these two numbers. So there's at least two answers, one in quadrant 1 and one in quadrant 2. And that would be those two angles. Clearly the one I need is the first one, pi over 3. So my angle range is from pi over 3 to pi over 2. Once I have that, it's actually fairly easy. Because the two regions that are overlapping are defined for the exact same angle range, I'll use only one integral. And since I want to use the entire region between the circle and above the line, I'll only go from pi over 3 to pi over 2 and double to get the whole thing. So it's 2 times the integral from pi over 3 to pi over 2 of 1/2 the difference in the squares of the radii, where the larger radii squared comes first. Now I'll just do this integration. So just distributing the 2 and the half, canceling and squaring as I need. And then using the half angle formula for the sine squared to cancel the 16 again, 8 times the quantity. And then multiplying the 8 through. And then integrating each piece and evaluating at the bounds. That's your answer. That would then be the region, the area of the region that's within the circle and above that line. Now, because a point, though, can have many different polar representations, extra care must be taken whenever you want to find the points of intersection between two curves expressed using polar coordinates, or if you wanted to just determine if a point is on a graph. For example, if you look at the points of intersection between the curves r equals 2 and r equals -2, by the traditional method, we would just set the r's equal to each other, giving you 2 equals -2, which is clearly impossible. That would imply then, for most people, that the curves don't intersect. But they represent the exact same circle, centered at the origin with radius 2. They actually intersect everywhere. So the problem is because these points have multiple representations, and in the first representation, the radius is always 2. In the second representation, the point is the radius is always -2. So they can never have the same coordinates. But they can refer to the same point. So curves can intersect. They just have different representations of those points where they do intersect. One way to maybe fix the problem, doesn't actually always work, but maybe one way to possibly fix it, is to take the point r comma theta in one of the equations and just replace it with one alternate representation of that point. The common one is that for any point r comma theta, you can also represent that point as -r comma theta plus pi. Look what happens if you do that here. Take the second equation, r equals -2. And there, replace every r with -r, replace every theta with theta plus pi. You would then get that equation. Notice then you can multiply both sides to get, well, just r equals 2. So obviously the equations are exactly the same everywhere. So that means then that the solution would be they intersect everywhere. You can also use the graphs and symmetry to find other intersection points. So if you look at the graph of r equals the square root of 2 and r equals 2 times the cosine of pi over 3, if you just set the r values equal to each other and solve that equation, you'll get one solution at least. That's where theta would be 3 pi over 4, which means you would get this point of intersection. But you actually won't ever get that one by just setting them equal to each other. But if you look at the graphs, you can see the graphs are symmetric with each other with respect to the polar axis. So then if there's an intersection point square root of 2 comma 3 pi over 4, then there has to be an intersection point at square root of 2 comma 5 pi over 4, because the angle between the pole, that point, and if you think of it the negative x-axis, that angle is pi over 4. So if you just start at pi and increase by pi over 4 to get 5 pi over 4, that has to be a location of another point of intersection. That does not mean that this point, though, satisfies both equations. It doesn't. This point will not satisfy this first equation. But if you take this point and find an alternate representation of it, and there's an infinite number of them, one of them actually will satisfy that equation. I'll leave it to you to try to figure out which one. Let's move on to arc length. Now, assuming that r as a function of theta has continuous first derivatives on the angle range from alpha to beta, and the point r comma theta traces out a curve exactly once as theta runs from alpha to beta, then we can evaluate the arc length of the curve just by using a parameterization, because r is a function of theta, and since x and y are r times a cosine or a sine, then actually x and y are both just functions of theta. So it's a parameterization of the curve. So we can use the parameterization formula to get it. The arc length then would then be the integration from alpha to beta of the square root of the sum of two squares, which are derivatives. In each case, it's dx over d theta or dy over d theta. But we know what x and y are in terms of theta, so I will leave the algebra to you. Just take the derivative of this x in terms of theta, take the derivative of the y in terms of theta, square it. You'll wind up getting 4 terms, and if you add up like terms and use the Pythagorean identity, sine squared plus cosine squared equals 1 twice, you get this simpler formula, that the arc length is given by the integration from alpha to the beta of the square root of r squared plus the derivative of r in terms of theta squared. Let's go ahead and find the arc length of a circle given by r equals 2 cosine of theta. I've provided the graph, and notice that the radius is 1, so the arc length is just a circumference, so the answer should be 2 pi when we're done. But you know that the circle, when centered at the origin, you need to go around from 0 to 2 pi to go through all of it. So you might think we have to integrate from 0 to 2 pi. But that'd be wrong, because if you look at the polar ray and rotate it through an angle of somewhere between pi over 2 and pi, the positive direction is going into the second quadrant. But the point, though, is not there. The point is in the fourth quadrant, so the radius is negative. So we only need an angle range from 0 to pi to trace the circle out once. If I went through 0 to 2 pi, I would do it twice. I'd get twice the arc length then. Now we know that, though, just find the integration by going from 0 to pi of the square root of r squared plus dr d theta squared d theta. And we know what r is, and we can easily find its derivative then, so I just plug things in. But then I can square each of the components, giving me this new integration. And I'm factoring out the common factor of 4, so you can see that the cosine squared of theta plus the sine squared of theta, that'd just be 1, leaving me with the square root of 4. So I get the integration from 0 to pi of 2 d theta, and that's just 2 pi. That would then be the arc length, as we knew it would be. And that's how to compute area and lengths in polar coordinates.